Okay, let's talk about stoichiometric calculations. Now, before you can really do this, you have to be able to do the mole conversions we talked about in 6.1. So if you need to, go back and watch that video first, and then once you feel comfortable with those, you'll be ready to do stoichiometric calculations. Okay, so first let's talk about what stoichiometry is. So in 6.1, we talked about conversions between moles and grams and particles, but for one substance. But now we're going to talk about looking at a balanced equation and figuring out if I have a given amount of reactant or product, if I have a reactant, how much product can I make, or how much of another reactant do I need, and if I have amount of product, how much reactant do I need to make that product. So let me give you a simple example. So in the discovery, we talked about making cookie sandwiches. So 2 Nilla wafers plus 1 marshmallow gave us 1 cookie sandwich, represented by W2M. So using this balanced equation, it's like a recipe. If I have 100 Nilla wafers, I know I need 50 marshmallows and I can make 50 sandwiches, okay? If I want to make 75 sandwiches, well then I know I'm going to need 150 Nilla wafers, okay? Chemical reactions work the exact same way. It basically provides a recipe for the reaction. So for example, if I want to make 100 molecules of water, that means I need 100 molecules of hydrogen, and I know that I make 2 molecules of water for every 1 oxygen molecule that I use, so I need 50 molecules of oxygen. Okay, so the balanced equation just gives you a recipe, okay? For every 2 molecules of hydrogen, I need 1 molecule of oxygen, and I produce 2 molecules of water, okay? Now, we talked in Unit 5 about the coefficients of balanced equations, and back in Unit 5, we might have looked at this first equation and said, okay, for every 1 molecule of methane, CH4 that reacts, I need 2 molecules of oxygen. And when I react those, I'll produce 1 molecule of CO2 and 2 molecules of water, okay? You could also say, because it keeps the ratio the same, that I react a dozen methane molecules with 2 dozen oxygen molecules to produce a dozen CO2 molecules and 2 dozen water molecules, okay? But remember, a mole is the same as a dozen, it's just a counting word. So I can also say that I react 1 mole of methane with 2 moles of oxygen to produce a mole of CO2 and 2 moles of water, okay? So these coefficients in the balanced equation tell me how many moles I need for a reaction. So let's fill this in. If I react 1 mole of methane, I'll need 2 moles of oxygen for full reaction. I'll produce 1 mole of carbon dioxide and 2 moles of water. In this next example, again, I'm going to use the coefficients of the balanced equation. So if I react 2 moles of C2H6, which is ethane, I'll need 7 moles of oxygen for full reaction. I'll produce 4 moles of carbon dioxide and 6 moles of water. Okay, so we're going to use those coefficients to give us what's called a mole ratio. Okay, so let's look at another equation. So this says how many moles of nitrogen are produced when 4 moles of ammonia, which is NH3, react. Okay, so from this balanced equation, if I have for every 4 moles of ammonia, I require 3 moles of oxygen, I produce 2 moles of nitrogen, and 6 moles of water. Okay? So if I have 4 moles of ammonia, the problem is asking me how many moles of nitrogen are produced. That'll be 2 moles. And again, I'm getting that from the balanced equation. Now in the next problem, it says how many moles of water are produced when 2 moles of ammonia react. So you might be able to reason this out and say, okay, well, half of the amount of the coefficients reacting, so I'll produce half the amount of water. But sometimes it's not quite as neat and tidy as that. So one way that we can use to solve these problems without just trying to reason it out in our heads is dimensional analysis. Okay, so I'm given 2 moles of ammonia. I'm trying to find the number of moles of water that will be produced. Okay, so from the balanced equation, I know that for every 4 moles of ammonia, I produce 6 moles of water. Okay? So from there, I can solve and see that I'll produce 3 moles of water. This is called a mole ratio. And this step will allow us to do something we haven't done before in dimensional analysis, which is convert from one reactant or product to another reactant or product. Okay? So every problem we do in this topic is going to involve a mole ratio because we're going to start talking about one substance and finish the problem talking about another. Okay, so every stoichiometry problem is going to have these 5 steps. First, we have to start with a balanced chemical equation. Now, oftentimes that will be given, but if not, we'll need to write it. Okay? I think step 2 is helpful, but it's not mandatory. We can figure out what parts of the equation we're using and cross out the rest, just so that they don't distract us and we don't do needless conversions. Now, whatever we're given, we have to convert our given units to moles. Okay? Now, if we're given moles to start with, obviously we can skip that step. Once we have moles of our starting substance, we'll use the mole ratio to convert from the substance we're given to the substance that we want. And finally, if the problem asks us for something other than moles as our final answer, we'll have to do that conversion at the end. Okay, so let's look at this example. All right, and keep those steps handy because we're going to refer back to them. Okay, so in this problem, we have a balanced equation. So that's good. Now, it says if 2.35 moles of ammonia react with sufficient oxygen, how many moles of water will be produced? Okay, so we're given 2.35 moles of ammonia, and we're trying to find moles of water. Now, this sufficient oxygen thing can distract people, but all that means is that I have plenty of oxygen and I don't have to worry about it. Okay, so the things that we're looking at in this equation are ammonia and water. And we can kind of ignore the other things, right? They're not participating in this problem. All right, so I'm starting with 2.35 moles of ammonia, and I'm trying to find moles of water. All right, so I have my balanced equation. I figured out what I was working with. So now my next step, step 3, is to convert my given units to moles. Now, in this particular case, I don't have to do that because my given's already in moles. So that means that I can move on to my mole ratio step. Okay? So I'm going to take moles of ammonia and put it in the denominator. And I could convert to moles of anything else, okay? But I'm going to look at what I want in the end, which is water, and I'll convert to moles of water. I could convert to moles of oxygen, I could convert to moles of nitrogen, but it's not going to help me in this particular case. Okay? Now I'm going to look at my balanced equation, and I'm going to use the coefficients to figure out my mole ratio. So from the balanced equation, I know that for every 4 moles of ammonia, I produce 6 moles of water. Okay? So when I calculate that, my final answer is 3.53 moles of water. And I don't know why that disappeared, but I'll put it back. Okay? All right, so okay, this problem says how many grams of oxygen gas are needed to react with 0.521 moles of iron. All right, so I have moles of iron. I want grams of oxygen gas. Okay? So I have a balanced equation. Now, I'm starting with moles of iron, and I want grams of oxygen. Now, if you look at the balanced equation, you'll notice that both things that I'm working with in this problem are reactants. That's fine, okay? Because sometimes if I know I want to react all that iron, it might be really useful for me to know how much oxygen I need. Okay, so my next step, now that I've identified what I'm working with, is to convert my given units to moles. Now again, I don't have to do that because this is already in moles, so I can move on to my mole ratio. So I'm going to take moles of iron and put it in the denominator. And when I'm selecting a unit for the top, I know it's going to be moles because that's my mole ratio. I could convert to moles of oxygen, or I could convert to moles of iron 3 oxide, but since I'm asking for oxygen in the end, I'm going to convert to moles of oxygen here. Okay? Now I need to put in my numbers. From the balanced equation, I know that for every 3 moles of oxygen, I need 4 moles of iron. Now, I've done my mole ratio, so my last step is to convert to my desired units. In this problem, I do have to do this because it's asking me for grams in the end. Okay, so I'm going to take moles of oxygen and move it down and convert to grams. Now, I have to ask myself, can I convert from moles to grams? Well, sure I can. I'm going to use the molar mass from the periodic table. Okay? So it's O2, so you have to be careful. You have to make sure you take the mass of oxygen and multiply it by 2. So it'll be 32.00. And your final answer here will be 12.5 grams of oxygen. And because I started with 3 significant digits, I rounded to 3. Remember that leading 0 here does not count. It's not a significant digit. All right, let's do another. And if you feel confident like you can try this, go ahead and pause and try it and check your answer. All right, so how many grams of water can be made from combusting 32 grams of methane gas? Now, the first thing you're probably going to notice here is that we don't have an equation like we've had before. Okay, but from Unit 5, you know how to do this. All right, we're combusting methane. So we know that one of our reactants is methane. Since we know it's a combustion, we know the other reactant is oxygen, and our products are carbon dioxide and water. Now we have to balance it. So remember, we balance these in the order carbon, hydrogen, oxygen. Carbon is balanced. Put a 2 here to balance hydrogen, and a 2 here to balance oxygen. Okay, now, we're given 32 grams of methane gas. We're trying to find grams of water. So, I have a balanced equation. I've identified what I'm working with, methane and water, and I can ignore everything else. Now I have to convert my given units into moles, and I do have to do that step this time because I'm starting with grams. So I'm going to take grams and put them here and convert to moles. All right, so then I have to ask myself how many grams are in a mole or moles are in a gram, and I know that to get between grams and moles, I have to use the molar mass from the periodic table. So the molar mass here is 16.05, and the units are grams per mole. So that means there are 16.05 grams of methane in 1 mole. Okay, I have moles. So my next step is the mole ratio. So I'm going to take moles of methane and move it here. And again, I'm going to choose to convert to moles of my desired substance in the end, so water. I'll get the numbers for my mole ratio from my balanced chemical equation. And now I have moles of my desired substance. So my final step is to convert to my desired units. In this case, it's grams. So I'm going to take moles of water and move it down. And I know I can convert from moles to grams, again, using the molar mass. So for water, when I add them all up, there are 18.02 grams of water in 1 mole. So 18.02 grams of water in 1 mole. And my final answer is 72 grams. Now, since I started with 2 significant digits here, I'm going to round to 2 significant digits there. Okay, one last problem, and we're going to use molecules this time. Okay, so here we have a balanced equation, which is nice. It says if 12.6 grams of sodium is added to water, so we're assuming we have enough water, how many molecules of hydrogen gas will be created? Okay, so I have sodium and hydrogen gas that I'm working with. I'm going to start by writing what I'm given. And my next step is to convert my given into moles. I'm also going to write what I'm going to in the end, and I'm going to abbreviate molecules as joules for space. Okay, so I have to convert my given into moles. So I take grams of sodium and move it down. I know from the periodic table that there are 22.99 grams of sodium in 1 mole. Now I have moles of my starting substance, so I'm going to do my mole ratio. So I'll put moles of sodium here. And I'm going to put moles of hydrogen here because that's my desired substance in the end. Okay? So for every 2 moles of sodium, I produce 1 mole of hydrogen. And again, that's from the coefficients of the balanced equation. And finally, I have to convert to my desired substance. Now here I want molecules. So I'm going to put moles of hydrogen here, and I have to ask myself, can I convert from moles to molecules? Okay, if you go back to 6.1 and look at that diagram, of course you absolutely can, and we're going to use Avogadro's number to do that. So Avogadro's number says that for 1 mole, there are 6.02 times 10 to the 23rd items, whether that's atoms, molecules, elephants, doesn't matter. Okay, 1 mole contains 6.02 times 10 to the 23rd molecules. So when I do my final calculation, I'll get 1.65 times 10 to the 23rd molecules. This is the kind of topic that only gets better as you practice it. So if you're feeling uncomfortable with the material, definitely practice it. I have extra practice for you if you want it, and of course come for help if you need it.